Okay, well, this is Mark, and in this video, I'm gonna do a couple of examples related to power and energy and efficiency. The first one is something that's gonna show up on our quiz in the next week and on the homework. Calculate the power exerted by a person who lifts a 100 Newton weight 2.2 meters above the floor in 1 second. So I've got a bunch of information given there, and I need to figure out what to do with it. Um, so the data I've got is 100 Newton weights and 2.2 meters above the floor in 1 second. And the thing I'm trying to find is the power. All right, so let's try and remind ourselves what each of these things are and how that relates to what we're trying to do. So power is the rate at which energy is used. So that is how much energy, or the work done, divided by the amount of time it takes to do that work. All right, well, I know the amount of time. It's going to take 1 second to do it. Do I know how much work is done in lifting that object up? Okay, so I know, I'm going to put some check marks in here. I know the time, that's the 1 second, but I don't know the work. So let's figure that out. Work. That would be the amount of energy that is expended in lifting that 100 Newton weight by 2.2 meters. All right. Well, to figure that out, I need to know to lift an object up in the air, that is the weight of the object times the height that you lift it up to, times the change in elevation, times the height. All right, do I know that? 100 Newton weight, that's how much it weighs, and 2.2 meters above the floor, that's the height. So yeah, I do know those two things. I know the weight, I know the height. All right, so my plan is I'm going to calculate the work by taking the weight, 100 newtons, times 2.2 meters. Then I'm going to plug that in up here for the amount of work done in lifting the object and divide it by the 1 second to find the power. All right, so the work is 100 newtons times 2.2 meters, which is 220 Newton meters. Now, Newton meter there's a shorthand name for that particular combination of units. That is also called a joule, which is abbreviated with a capital J. So that's 220 joules of work, or 220 joules of energy that are used in lifting the object up. So I know the work. I know the time is 1 second, so the power is going to be the amount of work divided by that time. That's 220 joules expended in 1 second. Well, dividing by 1 doesn't really do very much, but so you can see that the result is 220 joules per second. So you have to use 220 joules per second in order to lift that object up in 1 second. That particular combination of units, joules per second, also has a shorthand name. It's called the watt, which is abbreviated with a W. So that tells you how quickly you're using energy in order to lift that 100 Newton weight, 2.2 meters above the floor, in 1 second. Okay, so now I want to talk a little bit about efficiency and exactly what that means and how we can use it to understand some things about energy conversions. So efficiency is defined as the amount of useful energy output divided by the total energy input. So writing that out more colloquially, you might say that's the same as it's the output divided by the input. And what that means is, say you put 50 joules into something. So 50 joules goes in, but you only get 20 joules back out. So you're trying to do some work. it takes you 50 joules that you put into it. You only get 20 joules of useful work back out. That would correspond to 40% efficiency, because 20 divided by 50 is 40%, 0.4. So you have to ask yourself, if you're trying to figure out the efficiency of something, how much energy did you put in? How much energy did you get out? Divide them and you get the percentage. So these are typical efficiencies for different kinds of processes. So an electric motor has an efficiency of 50 to 90%. And that range, which is a fairly big range, comes from the fact that different electric motors are built in different ways. So you can get up to around 90% efficiency out of an electric motor, but ones that are maybe not quite as carefully designed would get 50%. It also depends a little bit on how you use it. So if you're using a motor and like an electric motor in a car and slamming on the accelerator, that's not used in the most efficient way, and so you get lower efficiency. But if you use it carefully, you can get up closer to the maximum values. So that 50 to 90% means, let's say you put 100 joules in, so put 100 in. On the top end, if you are very careful, you'll get 90 joules out, and that corresponds to 90%. A wind turbine has 35 to 50% efficiency. That means if you put 100 joules in, you get between 35 and 50 out. So 50 is the maximum. You get 50% back out. Nice thing about a wind turbine is that the energy you're using as your input is in some sense free, because it's coming from wind, and generally speaking, people don't cause wind. That's coming from differential heating of the earth due to the sun. Okay, an incandescent light bulb. Compared to these other things we're looking at, an incandescent light bulb has a terrible efficiency. It's only about 5%. So that means if you put 100 joules in, you only get 5 out. So 100 in turns into only 5 of output. And that's partly because incandescent light bulbs get really hot when they produce light. So the energy that you want is the light energy, and the energy you don't want is the heat. But incandescent light bulbs, the way they work by creating heat, which is not actually useful, and so most of the energy you put in is wasted. 95% of it gets lost. A fluorescent light bulb, on the other hand, is about 4 to 6 times more efficient than an incandescent light bulb because it doesn't produce as much heat. So that means if you put 100 in, that turns into 20 to 30 out. And again, that range has to do with the different kinds of designs of light bulbs and exactly how you use them. A solar cell, that is a solar panel used for generating electricity, has an efficiency of 5 to 28%. So that means 5 to 28% of the input energy coming into the cell gets turned into useful electrical energy on the way out. And that's relatively low. It's a relatively low percentage of the amount that goes in, but again, that energy is essentially free because it's coming from the sun. So it's not as important that you use 100% of that energy, because all of the starting energy that you're using in a solar cell is free in a sense. And then an automobile engine, a gasoline engine, has an efficiency of 20 to 30%. So about 20 to 30% of the energy in the gasoline gets turned into useful energy of moving the car around. So that means 100 in turns into 20 to 30 on the way out. Okay, so now I want to think a little bit about those numbers for efficiencies and what it means for kind of a practical problem. So the example is thinking about the source to user efficiency. And the question I want to start off with, what's the total energy efficiency for converting wind energy, say in a wind generator, to light in a fluorescent light bulb? So I want to convert wind energy to light in a fluorescent light bulb. So let's think about what's going on there. We've got a wind generator, and here's my awful physicist's wind power plant. So you get wind that causes the rotor of the turbine to spin, and that generates electricity. That electricity gets sent through wires that go to your house. Here's my little house. And then in your house, that electricity goes into the light bulb. And the energy gets converted into light. So each step in that process, you're taking energy that started out as wind energy, that's air moving around. It gets converted into electricity in the generator. That electricity gets sent through a power line, many, many miles, usually, to your house. And then in your house, that electrical energy gets turned into light in the light bulb. So there are several different steps in which energy is changed from one form to another. Every time energy gets changed from one form to another, some of it gets lost. That's what those efficiencies are. Some of it gets turned into forms that we don't actually want, usually heat or waste of some kind, and some of it gets converted into the useful thing that we want. So each one of these steps involves a loss. So let's look back at that table from the previous page for a second. A wind turbine has an efficiency of 35 to 50%. All right, so let's take the best case number. So that means when that wind gets turned into electrical energy on the wind generator, you only keep about half of the energy you started with. Then that energy gets sent down a wire. Electrical transmission lines are actually pretty efficient. They do a pretty good job. For most of them, it's between 90 and 95%. So let's put down that higher number. 95% is the efficiency of the electrical wire connecting the generator to your house. And then in your house, that electrical energy gets turned into the useful thing you actually wanted, which is light in the light bulb. And again, looking back at that table, the incandescent light bulb the fluorescent light bulb has an efficiency of 20 to 30%. So we'll take the high number, and we've got a 30% efficiency of that last conversion into the thing we want. So there's 50% efficiency, and then a 95% efficiency, and then a 30% efficiency. Each one of those conversions involves a loss of some chunk of the energy that you started with. So how do you combine those things together to get the total efficiency of that whole process? Well, chaining multiple conversions together requires multiplying. If I want to chain those multiple energy conversions together, I have to multiply. So let's say I started with 1,000 joules of wind energy, and I lose 50% of it when I convert that wind energy into electricity with the generator. That means I now only have 500. And then I have that 500 joules of energy, which is now being sent down this power line. I managed to keep 95% of it. So I want to do 95% times 500. So 95% times 500, which is 475 joules. So I'm keeping most of the energy that I started with this time, from 500 to 475. And I got that by doing 1,000 times 0.50. And then that result gives the 500 times 0.95. And then I've got one more energy conversion where that electrical energy gets turned into light in the fluorescent light bulb. And there I managed to keep 30% of it. So I want to do that result, 475 times 0.30. And that one I can't really do in my head, so I'm going to go over to the calculator and do 475 times 0.3, and that's 142.5. Okay. $143 joules left. So I started with 1,000 and I ended up with 143 by losing half, then losing 5%, and then losing 70%. The net result of that is that basically you need to multiply each of those percentages together. 50% times 95% times 30%. So 50% times 95% times 30% ends up being 14.3%. So that's the combined efficiency of that whole process of converting wind energy to electrical energy sent down the power line, and then that electrical energy turned into light in the light bulb. Cool. So now what I want to do is think about comparing that 14.3% for the total efficiency of a wind power plant to what I could get from some other option I might have for getting that energy. So for example, I want to talk about what if I use a coal plant instead of the wind turbine? Well, what would change about this process if I was to use a coal plant instead of a wind plant? Well, the process, most of it would be exactly the same. I would still have the power lines. I would still have the house. I would still have the light bulb generating the light. The only thing that would change is the wind part of it. So I would have a coal plant at that step. So coal plant. So you'd have some big building with a bunch of smokestacks, burning coal, producing smoke, and generating electricity. And then that electricity that gets generated would again go through the wires, travel many miles to the house. There's the house, and then I would again have inside the house the light bulb. And this wouldn't change anything about the efficiency of the power line, nor would it change the efficiency of the light bulb. It would still be 95% and 30%. The thing that would change would be the efficiency of the wind plant. Coal plants are not quite as efficient as wind. So where a wind turbine can get 50% of the wind energy and turn it into electricity, a coal plant can take about 30% of the chemical energy in the coal and turn it into electricity. Now, right off the bat, you might say, well, why does anybody use coal plants? Well, it's because there's lots of coal, and they're, in some sense, relatively easy to build. And there's a number of trade-offs that one has to consider in thinking about different energy sources. So coal plants are less efficient, but there's other reasons that people use them. So let's calculate the total efficiency of this system that has the coal plant in it instead of the wind plant. So we've got the 30%, the 95%, and the 30%. And the way I combine those three to get a single efficiency of the whole process is you multiply the 0.3 for the coal plant, that's 30%, times the 0.95 for the power line, that's 95%, times 0.3 again for the light bulb. And then I'll go over to my calculator and calculate that. You see I already typed that in. 0.3 times 0.95 times 0.3 is 8.55%. So I'm going to round that to 8.6. Go back over here. I get 8.6%. 0.6%. So that's the total efficiency of this whole process that starts with the power in the coal plant and goes to the power line and then converts all of that energy into light in the light bulb. So it's about 6% less than the efficiency for the wind plant. So that's an interesting comparison, and that's the kind of thing that you can do. You can think about those total numbers for each step in the process. Each step, because it's a conversion of energy from one form to another, always involves some loss, where some of that energy doesn't get fully converted into the form that you want, and you lose some of it as heat. And different energy resources or ways of using that energy have different efficiency rates depending on exactly how they're built and the kind of care that you take in using them.